welcome again. Yesterday we were talking about 4-terminal resistance. Okay, so I think the idea will be more clear if we solve a number of examples with 4-terminal resistances. So this video we will dedicate for solving some problems. Okay. So let's consider. So the question is, consider a 2-terminal resistance. Consider a 1 ohm 2-terminal resistance, 2-terminal 1 ohm resistance which we measure with voltmeter ammeter method. And the contact resistance that means the terminal resistance can be up to say 0.25 ohm, 0.25 ohm. Okay, so this is the maximum terminal resistance or contact resistance that we can have. Okay, now so this is the data given. Now if we measure the resistance with voltmeter ammeter method, then what can be the measured value? Okay, so let's consider the circuit. So the circuit is like this. So we have this resistance which is Rx equal to 1 ohm, and it has 2 terminals. Okay, so we connect wires here. We put a voltmeter, and so this is the voltmeter V, and say the voltmeter resistance, that the voltmeter that we are using has a resistance of 1 kilo ohm, and the ammeter resistance Ra, say that is 1 ohm. Okay, so here we will connect the ammeter. So Ra is equal to 1 ohm, Rv is equal to 1 kilo ohm, and then we have the power supply. This is a rheostat with which we can control the total current I. So this current will be I. Okay, now the experiment will be as follows. Okay, so control this rheostat so that I is equal to say 1 ampere. Okay, so this voltage has some value, maybe say 10 volt. Okay, so control RH such that I becomes 1 ampere, and note the value of the reading of the voltmeter. Call that V, voltmeter reading V. So then the estimated value of Rx will be the voltmeter reading divided by the ammeter reading I. So, this is the estimated value. Okay. So, with this hat we mean this is the estimated value of Rx, not the true value. True value we know it's 1 ohm. Okay. So, what will be this estimated value? So, the question is Rx hat estimated value, what will be this value? Okay. So, we will control this rheostat so that so we know that this circuit resistance is here around 1 ohm. So, we can have some contact resistances here which is like 0.25 ohm, then another 1 ohm. So, this all these resistances plus this rheostat RH, they together should be in such a value so that the I, this current, is 1 ampere. Okay. So, under that condition, what will be the value of V? Okay. Now, this I is 1 ampere, and so we know that the contact resistance can cause say up to 0.25 ohm resistance in so this contact. So, as we discussed yesterday, any contact we will model it as like this. So, if we have a contact like this, so where many wires are connected through some screw or something, so we will model it like an ideal junction with resistances caused in this individual branches. Okay. So, similarly here we will get these resistances due to this contact, and this value can vary. So, these values, so call this R1, R2, R3, R4, R5, R6. So, note that R1, 2 up to R6 can vary, and according to the question, this their value can be 0.25 ohm at max. So, this is not a large resistance, it is a very small resistance, 0.25 ohm, but we are considering it with so much care because this unknown resistance is also small. Okay. So, now if so, what will be the voltmeter reading? Voltmeter reading will be how much? So, the voltmeter reading will be, so the voltmeter actually will measure the voltage which appears between actually it will measure the voltage which appear between these 2 points here and here. So, this voltage, so this will be voltmeter reading. Okay. So, let us first find out this voltage, call this V1, and then voltmeter reading will be slightly less than V1 because some current will flow and there will be some voltage drop. Okay. So, voltmeter reading will be somewhat less than V1. Okay. So, before we find V, let us find V1 is equal to how much. Okay. So, now how will be the value of V1? V1 is the resistance between from here to here. Okay. And this current, sorry, V1 is the voltage between these 2 points. This current is I. Okay. So, V1 will be I, this current which partly goes through this and partly goes through this. So it will be I multiplied by the equivalent resistance of this part. Okay, and that equivalent resistance will be Rx, okay, plus Rx plus R2 plus R4, they are in series, Rx plus R2 plus R4, okay, this 3 and then R3, R6, RV, they are in parallel. So parallel R3 plus R6 plus RV. Okay. So this will be the value of V1. Okay, now let's put the values. So I we know is 1 ampere. Okay, so 1 ampere multiplied by, so Rx is 1 ohm plus R2 and R4. Maximum value of R2 and R4 is 0.25. Okay, so we are considering the situation when these resistances are maximum. So then this will be 0.25 plus 0.25. So that means another 0.5. So 1 plus 0.5, it will be 1.5 in parallel with R3, R6, R5. So that will be 1 kilovolt plus, that means 1000, sorry, sorry, this is not volt, this is ohm. Okay, sorry for the mistake. So 1 kilo ohm plus 0.25 plus 0.25. So this will be 1000.5 ohm. Okay, so considering maximum values of contact resistances. Okay, now this 1.5 is much smaller than this 1000.5. Okay, there is a ohm. So the parallel combination will be approximately or almost equal to 1.5. So this will be 1.5 into 1 ampere. So this we can write as 1 ampere into 1.5, almost equal to this, which is 1.5 volt. So this is the value of V1. Okay, so this is the value of V1. Now the value of voltmeter reading. Okay, now the voltmeter reading will be V1 minus any voltage drop here and here, R6 across R6 and R3. Okay, and if I call this current is IV, okay, so which is a part of the total current, I, which flows through this voltmeter. So voltmeter reading is V1 minus IV times R3 plus R6, and this IV we can write IV as, so the voltage drop here from here to here is V, so we write V divided by this total resistance R3 plus R6 plus RV. So this is 1000.5 approximately, or you can write it as 1000. Okay, and so this is IV, and then this will be multiplied by R3 plus R6 is 0.5. Okay, so this is approximately then, so this is V1. Okay, so V1 minus V1, here we have 0.5 divided by almost 1000. So this is like V1 multiplied by 0.0005. Okay, so this is approximately V1. Okay, so voltmeter reading is quite close to V1, slightly less than V1, and V1 is 1.5 volt. So maybe the true value of the voltmeter reading will be 1.49 and very close to 1.5 because of this slight drop, and it's negligible. Okay, so this is voltmeter reading. So therefore estimated value of Rx will be will be how much? It will be V voltmeter reading divided by the current or ammeter reading. Okay, this will come out to be 1.5 volt by 1 ampere, which is 1.5 ohm. This is not same as Rx true value. So there is a huge error. Okay, now let's take another question. So another question, so our part 2, part B. Okay, if the contact resistances are say 0.1 ohm instead of 0.25 ohm as considered above, then Rx hat, estimated value of Rx hat will be how much? Okay, so now, so suppose this is like we are performing the same experiment, voltmeter ohmmeter method of voltmeter ammeter method of measuring resistance. We are doing the same experiment another day, but this day, so we connect these terminals differently, therefore these resistances come out to be 0.1 ohm instead of 0.25 ohm. They can be different, and for simplicity we are considering all of them simple for ease of calculus, all of them same, but that's for ease of calculation, but they need not be same. So this can be 0.1, this can be 0.05, they can be different. Okay, but now let's say they have a different value from the previous case. So what will be the estimated value of Rx? Okay, so we will use the same circuit. Okay, so now these values are 0.1 ohm. So this is 0.1 ohm. This is 0.1 ohm. Everything is 0.1. All these resistances are 0.1 ohm. So we are doing the same experiment. Okay. Therefore, we set RH so that I is equal to 1 ampere. Okay, and measure and record voltmeter reading. So what will be the voltmeter reading? Okay, so before we find the voltmeter reading, let's find V1. Now V1 will be how much? V1 will be this current I multiplied by this parallel combination of these two resistances. So we can write it as Rx plus R2 plus R4 as before. This in parallel with Rv plus R3 plus R6. Okay, so this is the V1. Now this we can write as 1 ampere multiplied by this value will now be 1 plus 0.1 plus 0.1 is 0.2, 0.2. This is in parallel with a larger resistance 1000 plus, so this will be 1000.2. Okay, so ohm. So this will come, now this is much higher than this, so this is approximately 1 ampere multiplied by 1.2 ohm, so this will be 1.2 volt. And then voltmeter reading, this will be V1 minus this drop here and here, so which is IV multiplied by R6 plus R3. Now this IV will be V1 divided by R6 plus R3 plus RV, okay, multiplied by R3 plus R6. Now this value is much larger than this value, so this second term we can ignore. This is approximately equal to V1, this which is equal to 1.2 volt. So therefore Rx hat will come out to be 1.2 volt by 1 ampere, which is equal to 1.2 ohm. Okay, so this is once again not same as Rx true value, or this is also not same as Rx hat, which is calculated in the previous day. Okay, so we see that this experiment is not reliable, because every day this can give different result. Now the next question that we will take is this. So next question, or question C, if we had used 4 terminal resistance instead of the 2 terminal one as above, then what would have been the value of Rx hat, that means the estimated value of Rx, considering 0.2 ohm, 0.25 ohm contact resistance. Okay, so now we are doing the same experiment with a 4 terminal resistance. So we will have 4 terminals like this. Okay, note that this is also a junction, but this junction is a permanent junction. In case of a 4 terminal resistance, this junction is a permanent junction inside the box, and therefore whatever resistance this junction contributes, this will also contribute some small resistances here, similarly here, but that's a fixed value, that's not going to change. That's why that is not the problem. That's an important thing to understand. Now let's consider this problem once again. So we have this ammeter, we have this voltmeter, okay, and the power supply with a rheostat that can control the current. So we will do the same experiment. So once again adjust RH so that I is equal to 1 ampere. So we are doing the same experiment. So this total current is 1 ampere. Now let's put all the contact resistances everywhere. So we will have a contact resistance here, here, here. Okay, we are considering only this contact resistances which are variable, and the permanent contact resistances that you can assume it's already part of this main resistance, because that's a constant value. So we can think of that is as a constant part of this main resistance. We need not consider that. Okay, so let's consider this experiment, and all these resistances, let me give them names for ease of reference: R1, R2, R3, R4, then R5, R6, R7, R8. Okay, you have so many contact resistances. This is RV equal to 1 kilo ohm, and RA is not required, but still this is 1 ohm, and this Rx, this resistance is 1 ohm. Okay, so adjust RH so that the current is 1 ampere, and now we have to find voltmeter reading. So voltmeter reading is how much? Okay, so voltmeter reading will be we can write it as this current I multiplied by, okay, so before we find voltmeter reading, let's find the value of the voltage which is between these 2 points, okay, V1, we'll call that V1. So consider these 2 points here, this, and the voltage between this is V1. Okay, so let's find V1 first. Okay, then we can find voltmeter reading. Now V1 is this total current I multiplied by this parallel combination of this resistances. So we can write it as Rx in parallel with R6 5 RV, R6 plus R5 plus RV plus R4 plus R3 plus R4 plus R3. Okay, so this is V1. I is 1 ampere, Rx is 1 ohm, and in parallel we have, this is 1 kilo ohm, so this is 1 kilo ohm, plus all these can be at max 0.25 ohm. So considering the worst case scenario where these are the maximum contact resistances of 0.25 ohm, so 0.25 plus 0.25 plus 0.25 plus 0.25, that will be 1 ohm. 1 plus 1000 is 1001. So this will be 1001 ohm. And then this will be approximately very close to 1 ohm. So 1 ampere multiplied by 1 ohm, this is 1 volt. Okay, and then voltmeter reading, this will be how much? This will be this voltage V1 minus this drops. V1 minus, if this current is IV, then IV multiplied by all these resistances, R6 plus 5 plus 4 plus 3. Okay, so this will be V1 multiplied by IV, we can write as V1 divided by all these resistances, which is R V mainly voltmeter resistance plus R6 plus R5 plus R4 plus R3, and then here we have R6 plus R5 plus R4 plus R3. Now this is almost equal to V1 minus, so this term you can ignore because we have RV, which is a large resistance, so this denominator will be 1001 and the numerator is just 1. Okay, so this is 1 over 1000, so we can write this as V1 divided by 1000. So this is approximately equal to V1, which is equal to 1 volt. Okay, therefore Rx hat will come out to be voltmeter reading divided by ammeter reading, voltmeter reading by ammeter reading, which is I. Okay, so this will be 1 volt by 1 ampere is equal to 1 ohm. So you see that this is same as Rx, where Rx means all the resistances starting from this point to this point, including this and even this, everything from here to here is Rx. Okay, but most important thing to observe is that, so let's take another question. What happens if so let me write it this way. So Rx hat will be equal to how much if contact resistances are are 0.1 ohm instead of 0.25 ohm as before. So what will be that value? Okay, so this is next thing to consider. Okay, so now we can basically do the same calculation. So what we will do, we will, since we can do the same calculation, we will copy it and now we will change the values here. Okay. So now let us put the actual values. So in this experiment, once again rheostat will be adjusted so that I is equal to 1 ampere. Now we have to find the voltmeter reading, but before that we have to find this V1, and V1 will be again just like this, same expression will hold, but now Rx, R5, this will be 0.1 ohm. So the denominator will become, instead of 1001, this will become 1000.4, because this is 0.1 ohm, this is 0.1 ohm, all these are now 0.1 ohm. Okay, so this becomes 1000.4, but this is again approximately same as 1 volt, because this is much lower than 1000. And then V1 will be this, same expression is true, and now this factor will change, this factor will become, the numerator will be 0.4 and this will, denominator will be this, but still this is a very small number, so we will ignore it. So this is once again approximately equal to 0. So V1 is still same, and therefore Rx will still be same as 1 ohm. It's not changing. Okay. So observe, this is the beauty of a 4-terminal resistance. Measurement is so reliable. We can repeat the same experiment every time my contact resistance will change, but my reading or the value of estimated value of this Rx will come out to be same. So this is the beauty of this this 4-terminal resistance. Now we will take another problem in this video, which will be the last problem in this video. So the next question is as follows. So the question now is regarding the shunt resistance of an ammeter. Okay, so this is related to the shunt resistance of an ammeter. So consider an ammeter with full scale deflection current is equal to say 10 milliampere. This is my favorite number. Okay, I always use this number because calculations become so easy. So consider an ammeter with full scale deflection current as 10 milliampere, and the meter resistance Rm, that means the coil resistance maybe is say 99 ohm. So we want to change the range. We want to change the range to measure up to 1 ampere. Okay, so first calculate. So calculate required shunt resistance. So this is part A. This is part A. So we will have more parts, but let's do this part first. This is the easiest. So we have a ammeter. Full scale deflection current is how much? 10 milliampere. We want to put a shunt. And shunt resistance is how much? That we have to find out. Meter resistance is 99 ohm, and we want to measure a current which is 1 ampere. So when 1 ampere current flows through this circuit, okay, if 1 ampere current is flowing through this circuit, then the meter should show full scale deflection current. That means when this current is 1 ampere, this current should be 10 milliampere, and if so, then the remaining current must flow here. So this will be how much? This will be 1 ampere means 1000 minus 10, so 990 milliampere. Okay. Now, so what will be the value of RS? Now we can write that this voltage from here to here, so this voltage, consider this voltage, this voltage from here to here, this we can write as V is equal to this current 10 milliampere multiplied by meter resistance Rm. We can also write it as this current 990 milliampere multiplied by this resistance Rs. Okay, so then from this two we can write that, now can cancel this milliampere, 0, 0. So here we see that Rm is 99 Rs, or Rs is Rm by 99, which will be 99 ohm by 99 ohm, sorry, by 99, which is 1 ohm. So this should be 1 ohm. This is simplest. Now part B, next part is if we use a two-terminal shunt resistance, okay, if we use a two-terminal shunt resistance in the above scenario, in the above problem, and if contact resistances can be at max, contact resistances can be at max 0.25 ohm, then in this ammeter circuit, then this ammeter circuit will be erroneous because of the contact resistances. So if we use a two-terminal resistance, which will have two terminals like this, and we will connect wires, okay, like this, and these two terminals will cause some resistances, some variable resistance, unknown resistance, here, here, and here, and here. Their maximum value can be 0.25 ohm, here, 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 etc. Okay. Now the question is, now these resistances, these variable contact resistances will change the calibration of this meter, and therefore this circuit will be erroneous. How erroneous that can be? Okay, so let's estimate that. So estimate how erroneous the above circuit can be. Okay, so we have this, let me draw once again. We have this ammeter, and we are connecting this with a two-terminal resistance. Okay, so this is inside a box, and we are joining this with wires, and the current will enter through this and will live through this. So this will be the ammeter, total ammeter circuit. Okay, And now, so how erroneous this ammeter is, considering that these resistances are 0.25 ohm. So 0.25 ohm, 0.25 ohm. So this is the maximum value that we can have. Okay. Okay. So how erroneous can, and this resistance, so we have chosen this resistance as computed in part A. This should be 1 ohm. Okay. Now let's estimate the error. Okay. So consider when, say, consider when 1 ampere current is flowing through this, what will be the reading of this ammeter? Okay, we can calculate that, or we can calculate in the opposite way. Say when this ammeter is showing 1 full scale deflection, then what is this current? Okay, so consider or let's find. So let's find the value of I, this is I, the total current, when the ammeter shows full scale deflection, full scale deflection. Okay. So note that since we have connected a shunt resistance with nominal value 1 ohm, we will think that when this ammeter is showing full scale deflection, this current is actually 1 ampere. So note that okay, so before that, so let us first solve this. Let's find the value of I when the ammeter shows full scale deflection. Okay, so for full scale deflection, ammeter current IA, call this IA, this will be 10 milliampere according to the specification of the ammeter. Okay, so this current is 10 milliampere. So what is this voltage? Okay, so then V will be 10 milliampere multiplied by Rm, which is 10 milliampere multiplied by 99 ohm. So this will be 990 millivolt. Okay. Okay, and then what will be this current? Call this Is shunt. Okay, then Is will be V divided by this total resistance, V divided by 1 plus 0.25 plus 0.25 plus 0.25 plus 0.25. So 1 plus 4 into 0.25. So this will be V by 2 ohm, and V is 990 millivolt divided by 2 ohm. Okay, so this will be how much? This will be 500 minus 5, so this will be 495 milliampere. Please check my calculation. Okay, so this will be the value of Is. Now I, this is same as Ia plus Is plus Ia. Okay, so this will be then 10 milliampere, Ia is 10 milliampere plus 495 milliampere. Okay, so this means this will be 505 milliampere. So when the ammeter shows full scale deflection, then I is 505 milliampere. So let's write, when ammeter shows full scale deflection, then I is actually 505 milliampere. So note this. But we think that the shunt resistance is equal to Rx, according to that notation, is 1 ohm. So if we forget by mistake the contact resistances. Okay, so if we forget by mistake the contact resistances, then we will think that the Rx is 1 ohm, and therefore we will think when meter shows FSD, meter shows full scale deflection, then, so this is important, we will think this is not true, then V is equal to, this voltage is equal to, once again 10 milliampere multiplied by 99 ohm, this is 990 millivolt, and therefore we will think that Is shunt current is 990 millivolt by 1 ohm. So this is 990 milliampere, and therefore we will again think that I is equal to Is plus Ia, which is 990 plus 10 milliampere is equal to 1 milliampere. So we will think that the current I is 1 milliampere, but because of the contact resistances, this current is actually 505 milliampere. So we will make an error of almost 50%. So we believe the current is 1 this is 1 ampere. The current is 1 ampere, but the actual current is 505. So we think at FSD I is equal to 1 ampere, but actually at FSD I is only 505 milliampere, half of this. So there is a huge error. Okay, so there is a huge error. So now if we define an error, say a percentage error, okay, so now this time we can define the percentage error as, say, true current, okay, minus the meter reading, basically meter reading means what we think the actual current is. So this we can call as meter reading. I mean, this is what we believe the value is, okay, and then let's divide it by meter reading. Okay, so this is percentage error. So error as a fraction of the meter reading. Okay, so you're not, I mean, you could have also divided this by true current. Okay, that's also, I mean, both estimates are used in practice. So then you can take a mod sign, okay, if you do not need, or you do not want the plus minus sign, then this value is almost like true value is 1 ampere minus this is 505 milliampere divided by 505 milliampere. So this is approximately, this will come out to be into 100%. This will come out to be approximately 100%. Huge error. Okay. Okay. Sorry. There is a mistake. So this is not 505. This is okay. There is a mistake. Let me correct it. So this true value, true current is 505 minus meter reading is 1 ampere. This is milli ampere minus 1 ampere divided by 1 ampere. Okay, then this will be, you can take a mod sign into 100%. Then this will be like 495 milliampere by 1 ampere. So this is into 100%. This is approximately equal to 50%. Okay, huge error. Okay, now last part, what will be the error if we use 4 terminal resistance? Okay, so this is the final part. Okay, so here we will now use a 4 terminal resistance. So this is my ammeter and I have a resistance which has 4 terminals. Okay, and this thing is in a box. And the 4 terminals are outside. Now it's important to know how to connect this 4 terminal resistance as a shunt to this ammeter. What we should do is this, we should, so carefully note this connection, very carefully note this connection. If you make any mistake, then you will have a huge error. The way we should connect it is like this. Connect the ammeter to 2 terminals and make the other 2 terminals as the inlet outlet of the unknown current. So current I will enter through this and will leave through this, and this is my entire ammeter. Okay, this is how you should connect it. So note the connection very carefully. Okay, so now what will be the error? So we know this resistance is Rx. Okay, so let's find the value of I when the meter shows full scale deflection. Okay, so when the meter shows full scale deflection, that means this current must be 10 milliampere, which is the specification of this ammeter. Then the question is, what is this value of this current I? Okay, so before we find that, and we may have these contact resistances here, 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 and here, and here. And let's consider all of them to be the maximum contact resistance, which is 0.25 ohm, point here everywhere 0.25 ohm, 0.8 everywhere 0.25 ohm. So all these contact resistances are 0.25 ohm. Okay, under that situation, what will be the value of I? Now before we can find the value of I, we need the value of the voltage between this point and this point. So we need the voltage between these 2 points. Okay, so now this voltage V, how much will be this voltage V? This voltage will be same as this current multiplied by this total resistance. Okay, and this total resistance is RA plus 0.25 plus 0.25. So this is this total resistance. Okay, this is okay, and then oh sorry, there are 4, 1 2 3 4, so this will be multiplied by 4. Okay, so we have a contact resistance of 0.25 ohm, 0.25 ohm, 0.25 ohm and 0.25 ohm coming everywhere. Okay, okay, and so what will be the value of this voltage? This is this resistance multiplied by the current, which is 10 milliampere, and then this we can write as RA is 99 plus this is 1. Okay, so multiplied by 10 milliampere, so this is 100 times 10 1000 milli, so this will be 1 volt. So V will be 1 volt. Okay, now if V is 1 volt, then this current IS will be V divided by Rx. This will become V by 1 ohm. So 1 volt by 1 ohm. So this will be 1 ampere, right? So this will be 1 ampere, and therefore I, which is Is plus Ia, this will be 1 ampere plus 10 milliampere. So this will be 1.01 ampere. So this is the value of I when the meter shows full scale deflection current. So when meter shows FSD, I is equal to 1.01 ampere. But we will think, but if we had calibrated the meter ignoring these contact resistances, because we do not know the value of the contact resistance, so if we will think okay, that for when meter shows FSD, then this voltage V between these 2 points will be how much? That will be 10 milliampere multiplied by 99. So this is the same calculation as before. 10 milliampere multiplied by 99. This is the voltage, and therefore, so we will think. So this is all we will think. Then we will think that Is is this V divided by 1 ohm, this Rx. So this will be 990 millivolt by 1. So this will be 990 milliampere. So we will think I is equal to Ia plus Is. This will be 990 10 plus 990 milliampere, which is same as 1 ampere. So basically we will think that this current is 1 ampere. That means that we will calibrate, or we will mark the full extreme right side of the meter, extreme right side of the scale will mark the extreme right side of the scale as 1 ampere. So we will mark the full scale deflection as 1 ampere, but actually full scale deflection means 1.01 ampere. So what is the error? So the error, therefore the percentage error, so we are calculating it as meter reading, and here meter reading minus true value, you can take a mod. Okay, so this will come out to be meter reading is 1 ampere, true value is 1.01 ampere, and divided by 1 ampere. So this will be 0.01 and multiplied by 100%. So here also into 100% into 100%. So this will become 0.01 by 1 multiplied by 100. So this will be 1%. See, the error is so small, only 1%. Whereas if we had used the two terminal resistance, which is here, the error was 50%. Okay, so this is the beauty of a 4 terminal resistance. So I guess I have spent long enough time in conveying you why 4 terminal resistances are useful, so useful. Okay, I have tried to give you numeric demonstrations in different scenarios. One practical scenario is use of shunt resistance to change the scale of an ammeter, where 4 terminal resistances are very useful. Otherwise, if we use 2 terminal resistances, we can have huge error. So I have tried to give you a lot of examples, and I request you to think thoroughly over this topic, because you will be using 4 terminal resistances again and again in your lab, I believe, but maybe you always thought, why should a resistance should have 4 terminals? Resistance means always it has 2 terminals theoretically. What these 4 terminals mean? Why do we call them as 2 of them as potential terminals, current terminals, etc.? Why 4 terminals? So I have tried to give you enough examples. Why is it so useful? Thanks for watching. Let's meet again.